Record. All right. So are we on day 11? I think we're day 11. Means we're in week 6. We're over a third of the way through this class. Can you believe it? No. So the first 5 weeks we covered multi-level modeling. Now for the next couple of weeks, we're going to cover longitudinal. We did cross-section. We introduced R. We reviewed single level regression. We've talked about clustered hierarchical multi-level modeling. Now we're going to hit logistic versions of doing multi-level modeling. And then the second half of the class is generalizing either with a GEE or a generalized linear multi-level model. So with logistic, if your outcomes is 0, 1, Poisson, if your outcomes account, or negative binomial if you have over dispersion, and some other kinds of models when your outcome's not normally distributed or your residuals are not normally distributed. So today we get to go into longitudinal. Tonight is due, what's due tonight? Homework 4. Homework 5 is posted, but don't download it yet. I've got to update it tonight to make it, because some things have changed year to year. I haven't gotten that one updated yet. So let me update the RMD for you tonight. I'll send you a message tonight or first thing in the morning saying it's ready to go. You could read it now. It's not going to change substantially, but you might want to hold off downloading it and really getting too much into it. It's going to be basically the same, but I just want to update it with the changes to the tech reg package and the performance package and some of those little tinkery things that have changed year to year. Other questions before we hit longitudinal on clustered on the homework discussion board, clustered information. Let's see. We had some really great discussion board discussion. So here is the one on for clustered data. So there was a lot about convergence. So it's just some high points. Failure to converge means you cannot interpret that set of results, but it doesn't mean you're done for. It can mean your model's too complex, or you need to simplify your model, or you need to center your variables, but sometimes it just means you need to try a different optimizer. There are dozens of optimizers out there. There's at least 3 or 4 that are standard. And if one of them doesn't work, try another. If any of them work, if say 2 don't work and 2 do work, the ones that do converge will always converge to the same set of answers. So if you can get 1 to converge, that's good enough. You don't need to look for 2 or 3 that work. Just get 1. Here is, and this is on the encyclopedia, and I posted it on a couple of your comments. There is a website and a Stack Exchange post about different optimizers you can try. The Nelder-Mead is the most common one that makes most situations run. It's not a guaranteed, but between the default and the Nelder-Mead, that'll cover a lot of the time. What were some other big things? Centering of variables. Grand mean centering is usually, now there's always exceptions to this. Grand mean is usually for continuous variables only. Most often if that variable's values in your data set don't already have a meaningful 0 point. So we shift what's the center, especially if the range of the values is like 10 to 30. No one in our data set ever gets a 0. So we'll want to shift it, the center, to a value that actually exists in our observed data set. Also, it's a good idea to think about centering if the continuous variables involved in any kind of interaction. That can be a single level interactions, a 2 cross-level interaction, a 2-way, a 3-way. If the other variable's categorical continuous, it doesn't matter. If a variable, continuous variables involved in an interaction, it might behoove you to think about grand mean centering. Don't have to, but it can be very helpful. Mostly it's helpful to center for interpretation and secondary it helps models converge if we have a variable that say the values is age. Maybe it's age of kiddos in elementary school. And if it's age in months, everyone's like 100 to 200. Zero's not in that range, and those are very big numbers. So if we center it at like an important age or the youngest age, at least we get our values in a more restricted, smaller size of numbers, and it will help the convergence not struggle so hard. If we have a categorical variable, we generally prefer not to center unless it's strictly a control variable. We don't care about interpreting. Interpreting a centered categorical variable is harder. So we tend to avoid it if we can. But again, there's exceptions to all these rules. Carter, you're looking like you're thinking hard. Do you have a question about that?
No, I just kind of always running through my head, like in practice, like what are the cases? Yeah.
Yeah, and it's hard for me to tell you, you always do this and you never do that because there's so many exceptions. In the best case scenario, you don't have to center. Now, group mean centering we haven't talked about yet, and I'm going to hold off getting too much deeper in that. I'm not going to do it today, but I will make a recording on group mean centering because that's a whole nother ball. That's when we're looking at the group's average having an impact on the outcome, not just on the individual, but on the group as a whole. And that's a little trickier. Okay. Interactions. How do you figure out how to interpret an interaction? What's pretty much the only way? Plot. It's the only way usually. It's with one single level, it's hard enough. With multi-level models, you pretty much have to plot these things. And it's good luck. I still can't do it. I don't even try. Oh, this was a good, Ariel brought up this really great comment. So if we are going to check multiple random slopes, one way we could do it is like this: minority and sector, both in the parentheses. Now, let me just say this. Should we have try a random slope for sector?
No.
Why not?
Because it's level 2.
It's a school specific variable. So there's only one value of sector for the whole school. So sector's effect should not change within school. So you should only, if this word school is in the parentheses, the variables in front of that vertical bar should be different for different people in the school, not the same for everyone in the school. But say we had two variables. Doing it like this lets minority have a random slope, sector have a random slope, and lets those be correlated with each other. The second way, and there should be another parentheses, I think right there, have minority have a random slope and sector have a random slope, but they are not correlated with each other. These are two different ways to have two random slopes. One, the first way is lets the random slopes be correlated. The second way has the random slopes being uncorrelated. Hopefully you have theory to guide which one of these makes more sense. If you don't have theory, fit them both and compare the fit with the Anova command to do the likelihood ratio test. Now, if in this case, they would differ on a fixed effect or a random effect.
Random.
They differ by a random effect. That covariance between the two random slopes is also random. So you'd want to fit both of these models with ML or REML.
REML.
Different random effects, use REML. And then when you do the Anova command, make sure you add refit equals false. Yeah, but that's what I would, if I didn't have theory to guide me, that's what I would do. So this is great that you guys are writing these things down on the discussion board, because then I remember to tell you on the discussion board and to bring up things that keep coming up in class. So even if you got your question answered in the discussion board, it might be helpful to go back later and read and see if there's something you missed that might answer a question that you were still thinking about or hadn't thought about yet. So yeah, Alejandro, I redid that link to those optimizers. I don't have them in the encyclopedia right now because I can never hope to have all of them. Maybe I should move some of that information over, but I just always click on that link and go over there and take a look at it. Yeah, group means centered. We'll do that later. Okay, I think those are the main things off the discussion board. I am currently grading your homework 2 and your homework 3. So homework 3 was the first part of this clustered math achievement school data set. I've got the first third of your assignments graded this afternoon, so I am working on those. Homework 2 was when you found your journal articles, one clustered, one longitudinal. Let me show you where I'm putting them on the encyclopedia. So the encyclopedia is undergoing constant change. So I've added the first chapter, I'm calling it learning resources, and I'm putting links. I hope to put articles, book chapters, YouTube things, a bunch of different helpful links there. 1, so that I can find them in the future. 2, so you can find them in the future. 3, I can show other people them in the future. There's the formula warehouse. And then number 3, I'm adding articles. So I'm going through those articles you guys submitted with homework 2. And I am organizing them based on if the clustered ones, the longitudinal ones, and I'm guessing there's some articles that would fit both. And so I'll show you, so for each article, and I've only gotten through a few of you yet. It's going to take me a while to get this all done this week. This is why you don't have a homework 2 score yet, because I'm scoring it as I go through them. So this was an article called Parent Couples Participation in Speech Language Therapy for School-Age Children with Autism Spectrum Disorder in the United States. Whose is this, I wonder? Candace? Yes. So here are the links, a public link in the USU full text, and I've created this table for basically all of them, the high points. So what did they call it? How many levels? What size of sample? What did they do about missing data, centering? What kind of steps did they do? How did they present their results? What software did they use? And if there's a nice table or figure, I'm plopping it down here. So this would be a good place where you could come back and say, I'm writing a paper, doing an analysis. Is there one on this list that's like mine? And how did they present it? How did they write it up? So this would be a resource for you and me both when writing a paper, some other ones to look at. Now, if I come across some that you submitted that I think are crappy, I'm not going to put them on here. Not that you'll get a bad score. You have no clue. But I'm trying to weed through the best ones to put up here as example articles. Okay. And I'll add some others that I've found. Again, this is a work in progress. It will be growing all the time. Did this table look familiar? If you look at this table now, does this look familiar to you? We've got the fixed intercept and all these factors, and down at the bottom we have our random effects. This last thing is their fit statistic. It's a BIC type measure. So this should start to look familiar as we're learning more. It'll be interesting to see there's lots of different software packages used, M+, SPSS, this HLM, you might have seen some of you, Stata. HLM is a standalone software that only does hierarchical linear models. So there's that section. Then I've also added, it's now numbered number 8, the effect size variance explained. So variance explained, R² type measures can get quite complex for multi-level modeling. And so I put together here some resources, journal articles, walkthroughs, web posts, things that explain the complexities of R² and R² like measures and what's good practice. So marginal versus conditional. I've got links to articles. So if this is something you want to read more about or come back to in the future, there's like a spot for it on the encyclopedia. So we'll hit this as we come up to it before, but I think this is, I put this at the top on purpose. This is from that analysis factor website. That there are lots of versions of R² that are and it's becoming more common, but it's not entirely agreed upon or is standard. There's lots of different versions of R² that you can do with a multi-level model. most of them you cannot calculate directly with software. Instead, you have to calculate get the variance components from your model in the tech reg or the summary command, and then calculate them by hand. Importantly, if you choose to report any one of the R-squareds or multiple ones, you should not only identify which one you're using, but provide some brief interpretation and or a citation to base it on. You can't just call it R-squared. You got to say R-squared for level 1 from Snyder and Boschker, or from whichever one it is, so that we can communicate with each other, transparent and reproducible. Okay. And there is, I've had this all along. It's a good reminder. I went and reviewed it today. After that effect size variance explained R-squared section, there's this SJ plot. At the bottom, there's model diagnostics for residual diagnostics. And so I come back to this all the time to get the code to do residual diagnostics. That was one of the last things you have to do in this assignment that's due today. So if you want to come back and look at this, it's there for you as well. I'm not going to be grading homework for tonight. So if you want to resubmit it at any time, that's fine too.
Sarah, when you say anytime, do you mean anytime tonight?
Yes, tonight. And I think it's due at 8 o'clock, but I'm not going to be grading it tonight. So if it's in before tomorrow, you're fine.
Okay.
Okay. Good question. Okay, so we've covered most of these multi-level models with cluster data. If there aren't any more questions, I'm going to start talking longitudinal. Okay, let's dive right in. Okay, I'm going to start with the example that Hawks has in chapter 5, which is one of your current reading. I think I have the discussion post is due in 2 days, right? On the chapter 5 reading on longitudinal. So this, and then if we have time, we're going to go back and do this autism example. I don't know why I have them in this order. But, okay, so this is, please stop me at any time to ask any questions, because you know I blah, 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 blah. So Hawks chapter 5 example. So this is looking at the GPA of 200 college students. The multi-level part is that each student is followed for 6 consecutive semesters. This is simulated fake data so that it behaves nicely, but it's based on some past research. So we have 200 students, each at 6 time points. And at each time point, we have their GPA. We also have their job status, which is measured hours worked. And then we have some time invariant covariates like the student's gender and their high school GPA. There's a variable called admitted we will not be using in this data set, just ignore it. Okay. So this is Hawks's data set. You can get it from his GitHub for the book. Read it in. It looks like this. So we have the student variable, which is 1s, 2s, 3s. So this is their student identification number. Then we have the occasion. So year 1, semester 1, year 1, semester 2, year 2, semester 1. It's not a very handy way to have this labeled. And then we have their current GPA. So if you look at this, the first 6 lines in this data set are all for subject number 1. So that each of their semesters stacked up. So their GPA went from a 2.3 to a 2.1 to 3.0, stayed at 3.0, stayed at 3.0, and went to 3.3. So that's the first person's. So GPA is at 6 different time points for every person. Now their job, 2 hours, 2 hours, 2 hours, 2 hours, 2 hours. It's constant for this person, but it's not constant for every person. Sex, this is a gal, I guess. So female, 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 female. All 6 time points. We're assuming that that's constant during the study period. This high GPA is not their highest GPA. This is their high school GPA. This GPA variable is their college semester GPA. So this is their average high school cumulative GPA. And then again, we're ignoring the omitted variable. So tabulating it up here. So I looked at job, the job variable. The job variable is either no job, 1 hour, 2 hour, 3 hour, 4 or more. But what do you notice about the no job? Look at these counts. Who had no job? No one. Who had 4 or more hours? No one. I think this is like a daily working. I don't know. I don't know how they rated it. Okay, so I wanted to take that raw data that we download from the website and prepare it. So data wrangling. This is your little daily tips on data wrangling. So if we look up here, student is an ID variable, but right now it's a DBL. What does DBL mean in R?
Continuous or numeric.
It treats it as a continuous numeric variable. That means it will add, subtract, multiply, divide, and average. Do we want to have the average student ID number? That doesn't mean anything. That's like their name for our intents and purposes, de-identified. So we probably want to make that a factor. Occasion, this first year, first semester, first year, second semester, that's really not helpful. We need to work with that. GPA is probably okay. Job is a factor. Might want to do something with that. Female is being treated like a factor. That's great. High school GPA is numeric. That's fine. So this is what I did. I took the student variable, that's their ID. I made it a factor so it won't try to average it, because that would make no sense. And then I took the occasion variable and I mutated or changed it to create a semester variable. So the semester variable ends up going 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 for each person. And to do that, I use this really handy command called case_when. So it's like doing a bunch of if-then statements. So it says, if occasion is equal to the text year 1, semester 1, then I am going to make semester be 1. But if not that, then if occasion is equal to this text, I am going to make semester be 2, and on down the line. So it checks the first qualifier. It says, is this true? That's what the double equal says. Is this equal? And if it's true, after the tilde wave, that's going to be the plugin value for this sem variable. And if this is not true, then the person goes on to the next step and it says, well, if it's not that, then is it this? And if so, we're going to plug in a 2. Now the job variable, we see with the job variable, it has levels no hours, 1, 2, 3, 4, but on either end, those factor levels are not used. That can cause problems when you go to fit your model. Just alert. If you fit a factor as a predictor, but that nobody is in some of the levels, it will screw up your model and you'll get an error message. So you need to drop the levels that are not used. And the wrangling way to do that is to take, right here, I said take the job variable and factor drop the factor levels that are not used. And notice it started as calling job and I'm resaving it still as job. It's the same variable, but I've just dropped the unused levels so that the models don't get freaked out that there's no one with no hours. And then job is equal to that text. So I'm going to change a new variable called hours that is just the numbers 0, 1, 2, 3. So it doesn't have all that hours part on it. And then I'm just selecting those variables. And then this arrange command is what sorts the data set. So I want them student 1, 2, 3, 4, and within each student sorted semester 1, 2, 3, 4, 5, 6. And when I do that, this is what it'll look like. So the first 6 lines are the first student. First student is female. Their high school GPA was 2.8. For each of the 6 semesters, all 6 of them, they were working 2 hours every time, and their GPA is this last column. Okay. This is what we call long format. When we did clustered analysis, we had one line per person because person was level 1. It was our lowest micro, smallest unit, person. When we moved to longitudinal or repeated measures, person is not our lowest level anymore because we have multiple observations per person. So now our lowest micro unit level 1 is the sample of observations. And now our level 2, the cluster, is the person. This is where it's different. The math is the same, but now person, instead of being the smallest unit, is a higher unit. So each person here has multiple lines. So each line is not a person, each line is an observation. So we have repeated observations per person. Now, we are specifically going to be looking at change over time. Not all repeated measures are looking at change over time, but we're going to focus on this example just for a moment. We're only going to think about how does GPA change across time. This is the traditional longitudinal analysis, change over time. So those observations have a sequence, the first, second, third, fourth, fifth, sixth. When we did students in classes, did the students have a sequence to them? Was there a first student, second student, third? Not really. They were just a group of students or a group of nurses. We could number them and organize them, but they didn't inherently have an order to them. Longitudinal change over time, the observations have a natural ordering in time. Time is our focus, change over time. Again, that's not always the kind of repeated measures you have. You can have repeated measures where you just have replication, or you have different conditions that are in a different order for different subjects. Right now, we're thinking about repeated longitudinal change over time. So let's see, person number 2 is male with a high school GPA of 2.5. Look at their job. They're working 2 hours and then 3 hours and then back to 2 hours. That changes. And their GPA changes, 2.2, 2.5, 2.6, 2.6. So it's important to decide what are our levels and what are our factors, our predictors, what's our outcome. So I'm going to switch to sharing a whiteboard. Okay, where did it put the whiteboard? Where did the whiteboard go? Share. Clicked whiteboard. Oh, I know. I have to move your pictures off of it. There we go. There we go. Get my fancy pen out. Okay. So at this point, we have my nice stick figure, my person. And within each person, we are doing multiple observations. We have time point semester 1, semester 2, semester 3, and on to 6. Okay, to decide on your levels, you ask, what are the samples? We have a sample of, fill in the blanks. We have a sample of
Students and observations.
We definitely have a sample of students. So the macro units are students, college students here. What's less obvious is that within each student, we have a set of observations. The micro units are observations, or we could call them semesters. Now, we might have chosen our students at random. Probably not completely at random, but we are going to assume that these students are representative of all students on which we want to generalize, even if we have a sample of convenience at some point. It does not feel always like our time points, our observations are randomly selected, because they truly aren't random. But we're hoping, like our students, that they are representative across time, the progression across time. Okay, so now that we've got our levels established, let's think about our outcome. What is the outcome we are tracking across these 6 semesters?
Is it GPA?
It is GPA. So our outcome is GPA. Outcome must be measured at the lowest level, and that's true for every multi-level model. Has to be. So we have a GPA at 1, 2, 3, 4, 5, 6. Okay. Now, what are the predictors, our independent variables?
At level 1.
Or 2. Let's decide.
Hours worked.
Hours worked. Is that a level 1 or a level 2 variable? It could be either, but in this situation.
I think probably a level 1.
Why do you say a level 1, Joey?
Because it gets measured each specific time point, which is the new level 1 variable, has a corresponding hours with it.
Hours worked is a level 1 variable because it is measured separately and could be different at each semester for the same person. Now, some people, it stays constant, but it is allowed to be different each semester. It is a semester specific measurement.
Sarah,
Yeah.
would it, because in the Hawks chapter, they talk about like the term like time invariant variables. Would a time invariant variable always be a higher level variable?
Yes.
Okay.
So level 1 predictors are time variant. They could change from time to time. They are time specific. Level 2 variables are, here in this case, they would be student. Oh my gosh. Student specific or time invariant would be a level 2 predictor. So in this scenario, what's something that applies to the student as a whole that does not change across time, is not allowed to change across time?
High school GPA.
High school GPA. That is assumed to be a static, student-specific measurement, only done once. Now, in this case, what did we make sex? We said sex, we are going to make it the same across time. We're only measuring it once. We're assuming it's constant time invariant. So in this case, sex would be constant. Now, you can all imagine sometimes variables can change, but it's, do we measure it one time, like the baseline depression? Even though depression could change throughout time, do we measure it once? And do we assume that it's static, or do we measure it multiple at every time that the outcome's measured? That's the decision here. So high school GPA and sex for this one are definitely a level 2 student-specific time invariant predictor of GPA. And hours worked is a time varying covariate, a level 1 predictor. Okay. I will take a picture of this at the end. I think we might be adding more to it. So I'm going to go back to R, or to the encyclopedia. Let's see, encyclopedia. Bring that to the front. And I'm going to put you guys back on my other screen. There we go. Okay.
Question just about the data there. Why do
Yeah.
we have two? Am I misreading something? Why do we have two, like the job hours columns? The one job one where it says 2 hours, whatever, and then just the hours column. Is there a reason?
There is a reason, and this is a good point. I'm glad you brought this up. Sometimes we want the textual labels, and sometimes we just want the number value, so we can treat it as a continuous variable. So sometimes it is helpful to have both versions of a variable around, the text labeled factor and a numeric just number part. So for the, if you are not sure what you need, definitely keep them both and name them different things so you can use whichever one fits your purpose. Sometimes plotting, it would be nice to have the full 2 hours there, but modeling it, if we're going to treat it as continuous, we want just the number as a DBL, a double floating point decimal continuous value. Okay, now here I've used this nice handy command, psych : head tail, and it will give you the head, the top few lines, and the tail, the bottom few lines, with this like spacer in between. And by default, I think it does the top 4, 6, and the bottom 4, but I said, oh, I want more, I want the top 10, and then it's just doing the bottom 4. This is just to give us a good kind of like look at the data set, not that we're doing anything with it. So here, each person comprises 6 lines. This is long format because we're going to have however many, we have 200 people, but we're going to have 200 times 6. We're going to have 1,200 lines in this data set. It's going to be very, very long. The other way to rearrange this data set is wide, and that would be 1 line per person. Now, wide format and long format, one is not good, one is not better, they're just different. And sometimes you want long, and sometimes you want wide format. So right for now, I'm just going to show you the code to convert it from long to wide. I'm going to make a separate video that you can watch on your own for going back and forth more fluidly. But here I want to take, based on this semester, 1, 2, 3, 4, 5, 6, I want to take all the time varying variables, job hours, GPA, and spread them across the row. And so the command is in the tidyr package, it's pivot wider. So I'm going to use the semester variable to tack on the under 1, 2, 3, 4, 5, 6 at the end of the names of the time varying variables, jobs, hours, and GPA. And I want to separate with an underscore. So now you notice student 1 only has 1 line. Their sex and high school GPA are constant, so we only have 1 of those. But their job, we have 6 of those, but instead of being on 6 separate lines, they're now 6 columns. And it goes, this is a bad view because it's like wrapped the line because it would have gone off the screen. And so then hours, we have the hours, since it's done 6 times, we now have them listed as 6 separate variables. Long format is what you need to fit your multi-level model with your lemur command, LMER. Wide is often more helpful for making descriptive tables. So here I'm using the wide format to make a descriptive table. The benefit here is in the wide format, there's one line per person. So we only have 200 lines. So our descriptive table will only have n equals 200. This is really good for making a descriptive table for demographics, person-specific, time invariant, where there's only one number per person. And I've split it by male and female and tested it to see if they're different. Here, if you have it in the wide format, to look at the change in GPA, you have to list all the GPA variables, which in wide format is GPA underscore 1, GPA underscore 2, 3, 4, on and on. And now we can look at this. So we have 200 people, students, just less than half are male and just more than half are female. Look at the original GPA. This is the first semester GPA. Men and women, are they different? Eyeball it. Maybe not. What happens over time? In general, let's look at the total column. What happens, oh, I can't highlight down, to these 200 students as a whole? What happens to their GPA over this course of the 6 semesters? If we look at the summary, 2.6, 2.7, 2.8, 2.9, 3.0, 3.1, steadily increases. And we can look at the same thing for men and for women. Eyeball, is there an effect of male versus female? Are males and females the same? They're not identical, but they're both going up. So the main effect would, for sex, would say males are always lower than female by a constant amount or a semi-constant amount. An interaction between time and sex would say that that gap changes over time. Either the gap widens or the gap shrinks. So we can investigate that. That would be a cross-level interaction because time is at level 1 and male versus female is at level 2. So that would be a time by sex would be a cross-level interaction. So I'm going to go back before we get any further into the whiteboard. Oh, good. It came back. All right. So there's one variable that we haven't written down here, and it's our measurement of time. Let's see. What's the color we haven't used so far? Orange. Okay. Time. Now, when you do a repeated measures ANOVA, who's done repeated measure ANOVA? In 6600 or some class at some point, I hope. In repeated measures ANOVA, it treats the time points as if they are always equally spaced. And it requires that everyone has all the time points. So all these time points have to be equally spaced. Is that always the case with every research scenario? What would be one where they would not be equally spaced? Does someone have a scenario that you've read about or been involved with that was not equally spaced repeated measures?
Like in our intervention study, like we basically have to work with parent schedules for when they're going to bring in their kids for testing. So they get tested on different days a lot of the time. So
do you try to do them weekly or monthly, or is it just?
It's pre-post follow-up. So it's not a ton of time points, but like that's like on our like transcripts and stuff like that. We like keep track of the dates because a lot of the kids don't get tested on the same day.
So this is a good scenario. Pre, post, follow-up. Pre to the post is one time frame. Now, let's talk about what you plan to do, not what actually happens first, and then we'll get to that. So, Carly, in that scenario, how long in general is it from pre to post in the one you're thinking of?
Well, that can also vary because we're basically like we could give kids the intervention and it's a certain number of sessions, but because kids will be absent and stuff like that, some kids will go a longer number of weeks.
So let's
Whereas
say
like the number of sessions will typically be the same.
So what's the preferred scenario? Pre to post is 6 weeks.
Probably closer to like half a year, maybe
6
5
months.
months. Yeah.
6 months. How long is it to the follow-up? Another 5 to 6 months?
I think it's 4 months.
4 months. Ooh, are those equally spaced?
No.
In the perfect scenario, we've got a 5 to 6 months and then a 4 month. Often it's pre to post is only like a short period of time, and then it's like an 18-month follow-up.
Mhm.
So they are planned to be unequally spaced. So a repeated measures Anova demands that you assume all gaps are equally spaced in planning and in reality. If it's supposed to be 5 to 6 months and people are within 1 or 2 weeks, is that close enough? Probably. But if it's like 6 months versus 3 months, are those equally spaced? No. Structured time means you have a planned set of gaps. So if you plan to have baseline and 6 months later your post, and then 4 months later your follow-up, that would be structured time. There is a structure that you are enforcing to the repeated measures. Now, unstructured is something that we did in the memory study for the dementia progression grant. So once people were diagnosed or determined to have Alzheimer's disease, they endeavored, keyword, to follow these people up every 6 months. Now, these are elderly people that you're trying to go to their home and do a 2-hour visit with a nurse. How often do you think that they were able to visit them exactly every 6 months? Not even close. Sometimes they're 6 months apart. Sometimes they're 12 or 18 months apart. A vast difference in the size of gaps. And they tried to follow them from when they got Alzheimer's till they died. So some people had 1 or 2 visits. Some people had 15. That is very unstructured times. Even if we plan to follow people every 6 months from identification to death, the number of time points vary drastically. The gaps vary drastically. Totally unstructured. Structured means you want to have 3 time points. Now you could treat it as unstructured and just do how many weeks are the gaps, and it would be different for each person. Structured means you treat everyone as having the first gap being approximately 6 months and the second gap being approximately 4 months. Give or take a little wiggle room. So you can have them unequally spaced or equally spaced. You can have them structured or unstructured. Those 2 sets of terms are not in any way the same as each other. Now, in this high school GPA study or college GPA study, we're going every 6 semesters in a row. We are going to treat them as structured. Everybody has 6 time points and they're once a semester. At the end of the semester, GPA comes out, end of the semester. Now, fall to spring is a different time gap than spring to fall, right? Because of that thing called summer. But we're going to treat them as if they're equally spaced for our first foray into longitudinal. Now, what did we say about centering continuous variables? Why do we often want to center besides interactions? What's the good thing about centering?
They're more easy to interpret.
Interpret because
You can
zero has
print
a
the average.
meaning we can center at the average. With longitudinal, we'll often center at the first time point. So instead of numbering these 1 through 6, often we'll number the first one at 0. So the intercept is at the baseline, the first instance. So instead of numbering them 1 through 6, often we would number them 0, 1, 2, 3, 4, 5. And doing so lets us center at that's essentially centering at the first semester. So the time of 0 means at the start, the first semester. Now, center does not mean middle. Center means the 0 point. They have to get used to that. But this sequentially numbering with the first time point being 0 and numbering after that treats all these if they're equally spaced and centering. So this is equal spaced time points, structured time points centered at the initial semester. This is the easiest way to go. It is not always the right way to go. There's one thing I asked you, I don't know if you guys remembered way back when you did homework 2, when you were looking for your articles, when you looked for your longitudinal article, I asked you how do they treat time, and you didn't have a lot to go on at that point. This is what I was getting at: structured, unstructured, equally spaced, not. And I will tell you, I've read 3 or 4 of them so far, of your longitudinal articles. Guess what? I can't tell in most of them. They didn't give enough information to tell. But if they're looking at, if you hear the word linear growth, that usually means centered at the initial time point, sequenced 1, 2, 3, 4, 5, equally spaced thereafter, usually. But this is why I wish, reading these articles, I'm like, I wish they told me what software, I don't care what software, but I wish they had provided their code and some output so it would be transparent and reproducible and clear to me how they treated time, because this is the thing that's least clear in a lot of these articles. Okay. So time. Okay, so time is our major predictor. We want to look at change in GPA over time. And this is different than in the studies we've done so far because we didn't have a sequence within our clusters. So if we want to know how does GPA change over time, then our main predictor of interest is time. If we want to know, what if our research question is, do males and females have a different trajectory over time in GPA? How would we look at that? A different trajectory across time, different for males and females. Time is an observation specific, time varying covariate. Sex is a student specific, time invariant level 2 predictor. So if we have time and sex interacting, that's a cross level interaction. Can you do this with an Anova? Kind of, but it doesn't do it right. Mixed Anova tries to do this by what's called pseudo replication, but this is a better way to do it. If you assume only random intercepts, you will get nearly identical results as a mixed Anova. But if you add random slopes or interactions with other covariates, yada, yada, it's going way beyond what a mixed Anova can do. Plus, what if someone in your study, it didn't happen in this play data set, but what if someone came to we got their data recorded for all their time points, except for we couldn't find them at the 3rd semester. Maybe they were overseas in the Air Force. Maybe they were on maternity leave. What if we were missing one of their semesters? We just couldn't get a hold of them. They didn't answer our calls. In Anova, what would we have to do with that person who had 5 of the 6 time points?
Drop them.
They're out. Can't use anything. In multi-level model, do your clusters all have to be equally sized? No. So you can have missing time points and still use that person.
So I know, question,
Yes.
because I guess I didn't remember, I'm forgetting some of the things we talked about with power. I mean, I knew we had to have a lot of groups to do these things, like maybe 20 groups or something like that, which are people. That seems easy. But six kind of level ones per group. I mean, that's enough to do it. That's
Oh,
fine.
Joey brings up a great concept about power and sample size. Huge deal, right? So usually we say we want a good number of units at each level. 6 seems small, which means we probably need more than 15 or 20 students. To offset only having 6 observations, we probably need 100 or 200 students. Remember, sample size is not one or the other, it's the combination of the two. So even though we only have 6 time points, we have 600 students that combines to make 1,200 semesters. Is that enough power? Well, it depends on the effect size, the ICC, sparsity, these kinds of things. So yes, could I do this with only 3 time points? You can, but I might need more than 100 or 200. I might need 300 subjects.
Then I take it, it could be kind of the same in reverse. For example, like if you were getting 100 measurements from something, per student, then you might not even need that many groups per se, maybe 10.
And this is why in psychology and other areas, behavioral research, when we do animal models, how many animals do we have? A few. And what do we do with those few animals? Lots and lots and lots and lots of cycles and repeated observations. The more repeats makes up for the less animals. Vice versa, more people in this case would make up for less semesters. Now, if you haven't yet, I highly suggest in the next day or two, you read chapter 5 so you can do your discussion post, chapter 5 of Hawks. He starts out in his introduction talking about measurement tools. When we're doing longitudinal, there's always a balance between how often and how many observations we plan and take. Those of you in psychology or areas, an IQ test. How often can you give someone an IQ test?
Only once every 6 months.
Why, Candace? For those of us that don't know.
Because it's like learned effects. They learn how to do different strategies, and a lot of IQ tests are very similar. And so then they're naturally going to do better if they remember the test.
So there's learning effects and memory effects that some measurement tools can only be given so often, or else they start to lose their validity. We also have things like, what about if we're going a large amount of time, say studying reading of children from ages 5 to 12. Can I give them the same reading test at age 5, 6, all the way up to 11 and 12? Why? Some of you are shaking your head no. Why can't I give them the same reading test?
Because they're all at different reading levels. There's different expectations for different ages.
So this is a complication of repeated measures, is we have to make sure that whatever our measurement instrument or measurement tool is, that it's calibrated so even if we're using a different reading test for different ages, that its score means the same thing. So that's why often we'll have standardized scores or age equivalent scores so that we can compare observations. So every scenario is different in choosing how many observations to do, how closely to time them. Now, could I do like midterm GPA? And so I'd have 12. If I did midterm mid-semester GPA and final GPA, then I'd have 12 observations instead of 6. That's more powerful, right? Any complications with using midterm GPAs and final GPAs?
My only question is, do you have to have complete the rest of the, like, would you also have to have complete like hours worked at those mid time point things, or only the outcome variable?
Whenever you have the outcome measured, you have to have all the level 1 time varying covariates measured as well.
Okay.
Can anyone think of a problem if I use midterm GPAs with the final GPAs?
I mean, I would think it would depend on like how the grading structure is set up in the class. Like if the final is like a significant portion of your GPA, then how they're doing at the midterm, it wouldn't be representative in the same way.
Are those calibrated the same? Does midterm GPA mean the same thing, or can it be compared directly to final GPA?
I wouldn't think so in a lot of cases.
Most courses probably not, if you think back to your undergrad classes. Yeah, so we have to, the timing, the number of time points, more is not always better either. If we are only looking at linear change over time, how many points do you need to make a good estimate of a line, a straight line? 2 points exactly defines the line. So if you want to also measure residual, not just true change, but allow for noise or residual variance, to do a straight line, you probably need at least 3 time points. It's better if you have 4 or 5, but do you really need 37 points to make a straight line? Probably not. What if we're trying to model a curve, something that has not linear, but quadratic growth or decay? For instance, my Alzheimer's patients, one of the things they do is at each time of these time points, approximately planned for 6 months apart, they give them a cognitive test and they get a score on this cognitive test and they forget they have it. So every 6 months, we don't have a learning effect because they forget. If we did it every day, they might remember, might have carryover effect, but every 6 months we're good, or longer. In dementia and Alzheimer's, if you haven't studied it, decline of cognitive skills is not straight. People with dementia, they start here and they dive. It's a slow at first and then it's a dive. It's a curved trend. How many points do you need to model a good curvature? 2? 3? More than 3. More. So the type of growth that you're trying to model or the type of growth you expect can also influence how many points or observation time points you want. Conversely, if you only have 3 time points, at most you can look at is straight linear growth or decline. To model a curve, you need more than 3. Now, not everyone has to have all of those. Some people can have 1 or 2. Some can have 10 or 12, which we did with the Alzheimer's study. That's okay. Do we need a break? I feel like we need a break. We're almost push ahead. Let's just push ahead because we only go till 6, right? It's 25 minutes. We can do it. Okay. We're not going to get to the autism example. That's okay. Although Candace, you'll like the autism example. I read back at it and I'm like, hey, I know what some of these things mean now. Okay, let's go back to our, okay. Pull your pictures over here. All right, okay. So let's do our first multi-level model with Logistic. Here's the good news. Everything you've learned before still works. The only difference is now people are not the lowest level, people are the higher level. Math still works, the code still works. So I'm going to fit my first lemur model, and it's a null model, so I'm going to call it 0, and I'm going to fit it with restricted maximum likelihood. Why would I fit my first null model with restricted maximum likelihood? So I can calculate the
ICC.
ICC, yay, we still do that. So here I'm looking at GPA with a fixed intercept and random intercepts per student. Now we have one, we're using the long data set because we have one line per observation per semester, and the semesters are grouped together by according to the student on whom they are measured on. So I can do my ICC, boom. What does this ICC tell me? There, I'll hide it.
36.9% of the variance of the outcome variable can be attributed to the students. Differences in students.
Yep. Over a third, 0.36 is more than a third would be 0.33. So more than a third of the variance in GPA is due to student differences. Over a third of the variance in the 6 GPA measurements is variance between individuals. 2/3 of the variance then is due to individuals changing across time. And there's our little row, because row is the shortcut for ICC. Okay, so here I've done it with REML to get the ICC. Now, what in the heck did I do here? I'm calling this fit 1 REML. What did I do differently? What did I add? Oh boy.
You centered semester on 0, or
I
you subtracted 1 to
one
do
from
that.
the semester number so that it's centered where 0 means the first semester. And that capital I means to internally do that in the model. So when it's fitting the model, it's taking semester and centering it at the first time point. Subtracting 1 from the semester number makes 0 be the first semester. Now, this is putting time as a fixed or random variable.
Fixed.
Fixed, how do we know it's fixed?
Because it's on the outside of the parentheses and we're doing REML equals
Outside
true.
of the random parentheses part. Okay, so here I'm redoing the ICC. Now this is different than before. Usually we do the ICC when we only have these ones as fixed intercepts, random intercepts. But with a longitudinal model, we often fit another null model with time as a fixed effect and redo the ICC. Now our ICC, it depends on if we do adjusted or conditional. This is the same language of marginal or conditional. This is like, depending on which one, it's about half. It's close to 0.5. The language changed different. So we say after accounting for linear change in GPA across semesters. After that, half the variance in GPA is attributable, that's weird, to person differences. Or we could say it another way, we could say half of the variance in initial GPA is due to student differences. Because this would be like time, we're accounting for time. So just the intercepts is left. So the intercepts would be the initial GPA. So when we have longitudinal models, there's often we'll fit 2 different null models. One, the way we're used to with just fixed intercepts, random intercepts. The second way, adding fixed effect of however we're denoting time. And here time is semester centered at initial semester. Then we're going to go ahead and start adding fixed effects. So fixed effects, we're going to use ML, so REML equals false. I've built it up first adding time and hours worked, high school GPA, and sex. Do I really need all these intermediate models? Probably not, but I'm recreating the textbook. So I did them all. Thank you, Hawks. So that I can put them together into this table. Okay. I've added some more fancy code in here if you ever want to know how to do this. Here is the default, just throwing in nitreg, the names of those models. But here I added a whole bunch of other fancy stuff to make it look like the Hawks table 5.3 on page 68 of your textbook. Because he doesn't show you how to get those numbers. I'll show you how to get them. Okay. So let's see, what can we see here? So here's our intercept, fixed intercepts in all of them. Okay, here's semester, that's our time variable. Now notice semester is centered at the first observation, first semester. Hours worked, and then those are our level 1 occasion specific time varying variables. Then I have high school GPA and sex, whether male or female. Those are our level 2 predictors. So Hawk says first you add level 1 predictors, then you add level 2 predictors. Okay. Then we've got our AIC, BIC, and our log likelihood. These are our fit statistics. Then we have our sample sizes, all of them, 200 subjects, people, 6 observations each. And then let's see, let's check out residual variance. What happens to the residual variance as we add more fixed effects? Moving over in the table. Adding more fixed effects, residual variance goes down. What happens to the student variance in Intercept? Does it go constantly down? Check this out. No model, we added 1 variable. What happened? It actually went up. Adding a variable increased variance. Ah! It doesn't increase residual variance, but it does increase the student to student variance in the intercept. And this can happen with multi-level modeling. And this is what can lead to a negative R squared by some of the ways of calculating R squared. So I just want to point this out. Yes, the residual variance will never go up, should never go up, but the random variance components for random intercepts and or slopes can increase because we're shifting around where the variance is attributable for. It went way down in the residual and it just happened to go up a little bit in the intercept. Now, of course, we can use that Anova command to do the likelihood ratio test. Let's see, what does this tell us about each of our models? As they increase in complexity, helps the model fit better. So far, what's our best model name? The third one, okay? And that has that, all of those 4 fixed effects. Okay, so variance explained by linear time at level 1. So this is this var core command, and then you can print it and you can get the variance components out. So here are R squared measures. There's Radenbush and Rourke. They're some of the first people that established multi-level modeling textbooks. They define R squared with this formula. You take, notice, what are all these sigma squareds? They're all have the little subscript E. E, sigma squared E means the residual variance. So Radenbush and Rourke said you just compare the residual variance, how much the residual variance goes down over what it stayed at. That's called the approximate R squared at level 1. Cox's formula 4.8. Snyder and Bosker, oh, I think I took their book home. They formulated their R squared slightly different. And notice these sigma squared, these first 2 have a little subscript E, that's residual variance, but what do these other sigma squareds have? U0, that's the random intercept variance. And sometimes that can go up and sometimes that can go down. So sometimes when you use Snyder and Bosker's formulas, you will actually get a negative R squared or even a 0 R squared. That's problematic. Most of the time, both of these formulas will give you approximately the same R squared. It's just in some funky situations they can disagree, and this one can actually be negative, so that's a problem. You can do R squared at level 2, and that's where we get this negative variance. So look at this formula. It only is looking at the change in random intercept variance. Now, in this formula, or this table, what happened to our student level variance between the first two models? It went from 0.057 up to 0.063. So when you subtract those, you get a negative number. And so this is the problem. So Radenbush and Rourke were the first ones to develop these R squares, but they have this kind of side effect of getting negative R squared, which makes no sense. So that's why Snyder and Bosker came up with their other version. That's all I'm going to say on that today. This will come back up, and we're almost out of time, so I don't want to like lay it on too thick, but the reason basically you get those negative R squareds is that the intercept only model overestimates the variance at the occasion level and underestimates the variance at the subject level. That's why we often fit that second null model that has time in it. And this chapter 4 in Hawks talks about this a little bit. Okay, so after we decide that we got level 1 fixed effects, level 2 fixed effects, what comes next? And fitting a model with no theory before cross-level interactions. Random effects. So we go from having just a 1 there to adding time. You always want to try whatever your timing variable is as a random slope, because we want to look at the overall trajectory, but assuming that different people have slightly different trajectories. That's where we do that. Now, in this case, I had to add a control statement, an optimizer change so that it would fit. And I checked it out. And what do we see? This is all of our fixed effects with only random intercepts with REML, and to which I added the random slope for our timing variable. These are both fit with REML, so I need, because they're random effects, so I need refit equals false. And what does this happy stars tell us? What does this mean? We do have random slopes for our timing variable. Now we can go to that cross-level interaction. I want to know, is there a different slope change over time for each male and female? That's our interaction. Now notice I put it here with a colon. Did I really need to do that? No, I could have done the asterisk, but I don't remember why I did that. Okay, so here are the models. And then here it is tidied up to look like Hawks's table 5.4 on page 80. So let's see, we've got our level 1, our level 2, and our cross-level interaction. What kind of stars are these? Where do these stars come from? Likelihood ratio test or something else? Wald test. And what does the Wald test tell us about the interaction?
Wald test.
Significant. But to trust it, I ought to not just rely on Wald tests. I should do a log likelihood ratio test. There, I did it. Boom. It is significant. So we do have an interaction. How can we interpret the interaction? Visualize it. Whether it's a 2-way, a 3-way, a cross level, a single level interaction, you plot it. So here's the quickest code. Interactions plot, give it the name of the model. The main predictor is semester 1, 2, 3, 4, 5, 6, except for we recoded it to be 0, 1, 2, 3. And then what's our moderator that it's interacting with is sex. And interval equals true does what? It's the bands on. Now, let me point this out. In our model, when we fit our model, every time we were talking about across time, we did the internally centering semester at the first observation. But when we do the plot, we just put semester. Because we internally centered time, when we plot it, we just say semester. And look what it did. 1, 2, 3, 4, 5, 6. It uncenters it when it makes the plot because you only internally centered it in the model. This is the easiest way to do this, I promise. Okay, so there it is, the easiest, simplest syntax. Here I've added a couple, well, let's look at this one first. Okay, what is the nature of this interaction?
The female student, both sexes increase their GPAs over time, but the female students increase more.
At the initial semester, females are slightly higher. Can't really tell if it's statistically significant because we have a little bit of overlap, but they start out slightly higher. But over the 6 semesters, even though males increase, the gap widens and females increase at a higher rate. Okay. Now, in our model, did we just have semester and sex? No, we had some other variables. Now, the other variables that were in our model, here's the other variables. High school GPA. It was not part of an interaction. Hours working. It also was not part of an interaction. But you can add it to this interaction plot by putting it as mod 2. So here I've added hours worked as mod 2, and I put in values 1, 2, 3, because those were the only ones that we saw in this data set. And it's going to make that plot for those working 1 hour, 2 hours, 3 hours. What do we notice as hours worked increase? What happens to GPA? It goes down. Does the shape of that interaction change at all? No. In fact, if we look up here at hours worked, the estimate is -0.1, -0.13. So that tells me for each additional hour work, GPA goes down 0.13 points. But the interact is not involved in the interaction. What about high school GPA? What's its estimate? A positive about 0.09. So what's going to happen if I move over in high school GPA? What's going to happen to that figure? It's going to go up. So to check, I added instead mod 2 at high school GPA, and I put in values of 2, 3, and 4 because that covered the span. And what happens as GPA goes up by a whole number, what happens to that whole plot? It goes up by 0.09. Now, do we really need all 3 of these panels? They're kind of redundant. What about these 3 panels? Kind of redundant. Really, if I'm publishing it, I'm probably at most going to put this 1 plot, because you can talk about main effects, just shift everything up or down a slight bit. They don't change the shape. Okay. Now, just in our last 5 minutes, effect sizes are a big deal. And one of the ways you can do effect sizes are R-squared, but R-squareds give you either R-squared is either how well the model as a whole fits, or you can use it to compare how well 2 models compare, adding or subtracting a term to kind of get a pseudo R-squared for a single variable. Another effect size is a standardized parameters. And I came across in the effect size package, this is new to me, a command called standardized parameters. And you just give it the name of your model and it plops out the standardized coefficients. In Hawks, he adds these to his table. Which table is it? I should have wrote it down. Oh, table 5.4. He just throws them to the table. I was like, how do I get those? Well, you just ask for them. And here are the standardized parameters. It even gives you a confidence interval around them. So hours worked, it's standardized. So an increase in a standard deviation of hours results in a decrease of 0.14 standard deviations in the outcome. This lets you compare the effects of the variables to each other. We look at these effect sizes, standardized coefficients. What's the most influential variable?
Time. Oh, sex, actually.
Gender.
What?
Gender.
Gender or sex, followed by semester and their interaction. Those three together account for most of the biggest effect sizes. Now, if you want to make R, the program, calculate your R squared values, you can use that performance package to do that. Now, if you just give it the model, it will only give you one number. If you add this by group equals true, it will give you the variance, proportion of variance explained at level 1. And it doesn't say level 2, it actually names what those levels are. Those are students. So 35% of the variance between students is explained by this model, but only 2% of the variance between observations within a student are explained. Okay, I'm going to stop there. So you can log off, or I'll stick around. Question and answer time. And if you're not burnt out from an hour and a half straight of me blabbing.
I had a quick question.
Yeah.
At the very beginning, when you defined the hours variable,
Hours.
I'm not sure if was that created in the dplyr package without creating it, without assigning it as an object somewhere before?
It becomes a call. Hours in the original data raw, it didn't exist.
Right.
It had the job variable. So to create a new, now when I did this one, job, I revised that variable and saved it over itself.
Mm-hmm.
For hour, in this step, mutate statement can either revise a variable and save it over itself, or it can revise a variable and save it as a new variable in the data set.
Okay.
So I'm taking the pre-existing job variable and creating a version of it that I am going to name hours. So the hours becomes a new variable within the data set.
I just didn't know that you could do that without telling R first that there's an object called hours and assigning it something.
No,
so the mutate can actually do that for you.
Hours is going to be a new variable that's going to have values. When job is equal to no job, its value is 0, and on down the pipe.
Okay.
Yeah, it's very handy if you want to recode variables in a complex way sometimes, this case when in dplyr mutate.
So it's mutating the data frame.
Yes.
Okay.
Yeah.
Okay, thank you.
Thank you. Oh, there went Jill. It's just
Hi,
you.
Jill. Okay, something I got to thinking.
Mm-hmm.
One, I was getting the levels, and now this longitudinal, it's kind of like we're rethinking of how levels fit for this longitudinal method.
Mm-hmm.
And I just had a little bit of a different question because I've been reading. I read a couple studies that actually use this mixed level modeling where they use these clusters to do a meta-analyses.
Yes, there's a whole chapter on that in Hox's book.
Oh, there is in this book?
Yes.
Because I guess I was just trying to picture what are the different, like, what becomes the levels then in a meta-analysis, because, cool, I didn't know there's a chapter. I'll just have to read it then.
chapter 11, actually. And we're not going to
Oh.
cover it in this class, but so if one way you can use it is if you have multiple, I've seen it used if you have multiple intervention groups per study or multiple outcomes per study. So you have multiple things nested under each study. So the study is the higher level, and the group of effect sizes, whether they're for different interventions or different outcomes, they are the in study.
Interesting. I see. I didn't think of that way. I guess I was just thinking one effect size per study, but that's true. There might be multiple for even you could probably do the control, like the control group would have.
Control versus intervention A and control versus intervention B.
Yeah. Okay.
Or what's the effect size for the Beck depression inventory? What's the effect size for the Beck anxiety score? Different studies have multiple effect sizes in them.
Cool.
And you don't want to treat them as if they're all different because they're all they share the common environment of that study. The other way I've used it is doing meta-analysis of what's called single subject design. Have you been involved in any single subject or N of 1? Is what they sometimes
No, not anything quantitative.
Yeah, so that's another place where it's, again, you have within each study multiple effect sizes or multiple values, and you don't want to treat them all as all the same, and you don't want to average them all.
Cool. I think it'll be really useful. Well, I'm gonna go. I noticed you're doing like a presentation, a seminar on the 28th on meta-analysis stuff. So I'm
one of, I think there's 4 of us presenting. It's going to be.
Oh, there's a bunch. Oh.
Finish my slides on that one. That's on my to-do list.
Yeah, I'm really thinking of going that route for my dissertation, because, you know, I guess it's a non-human subjects research method is one.
Yeah, and that's why we're doing that brown bag seminar on it. Is they're actually doing several sessions on non-face-to-face data collection type methods to get a dissertation done.
Yeah, and it gave me a chance to do a quantitative, really application type of work. So I might be able to use what I'm learning in this class, you know, that project. So
there is a package specifically in R for doing meta-analysis under the multi-level approach. It's called Meta 4. So it's one I'll talk about.
Cool. Well, and even pointing me that chapter, I'll dig into the chapter some. So
yeah.
Well, thanks as always, Dr. Schwartz. Nice to see you.
Yeah, bye.
Bye-bye.